Hello, this video includes information on strength of acids and introduction to Ka.
Let's talk about acids, and we're going to classify them as either being strong acids or weak acids. So when we look at an acid and we say that that acid is a strong acid, what we mean by that is it 100% ionizes in solution. Hydrobromic acid is an example of a strong acid. If we were to put it into water, 100% of it is going to donate its proton to the water. We're going to produce hydronium and bromide. Strong acids fully ionize. Okay, 100% reacts. That means that the conjugate base is so weak that the reverse reaction can't take place. Okay, so what do we mean when we talk about weak acids? Well, weak acids, only very small percentages actually ionize. So we're going to end up with an equilibrium. Okay, hydrofluoric acid is an example of a weak acid. Okay, well, it's an acid. It's going to donate protons to water to produce hydronium ions and fluoride ions. But because this is a weak acid, it doesn't fully ionize. That means that the conjugate base is strong enough that the reverse reaction is going to take place. So for strong acids, the reaction essentially goes to completion. For weak acids, it reaches an equilibrium. Strong acids and strong bases completely dissociate in water. Okay, here's our list. Okay, there are 6 strong acids and 6 strong bases that we need to be aware of. Okay, for strong acids, I'm actually going to do it in a little bit of a different order than this. I'm going to look at the binary acids first. So hydrochloric acid, hydrobromic acid, and hydroiodic acid are strong acids. Okay, they all have halogens as their negative ion. They're in the same group on the periodic table: hydrochloric, hydrobromic, hydroiodic, 100% dissociate. Okay, oxyacids: perchloric acid, nitric acid, and sulfuric acid are strong oxyacids. And we have to know this list. Now, strong bases, okay, they 100% dissociate in water. Lithium hydroxide, sodium hydroxide, potassium hydroxide. These are all hydroxides that have alkali metals as their cations. Put them into water, they 100% break up into ions. They're strong electrolytes. Calcium hydroxide, strontium hydroxide, and barium hydroxide are also considered to be strong bases. And these are alkaline earth metals with hydroxide. Okay, so when we look at weak acids, we're going to have an equilibrium that's going to be established, so we can write equilibrium expressions. We'll have equilibrium constants, and we can work with problems just like we can any other type of equilibrium. So here's a generic reaction. We have our acid, HA. This is just a generic anion, negative ion. And we put it into water. HA is going to act like an acid. It's going to donate its proton to water. We're going to produce hydronium ions and A ions. But because HA is a weak acid, we're going to have an equilibrium that's going to be established between the forward and the reverse reaction. Well, since we have an equilibrium, we can write an equilibrium expression. Now, we're going to use this little A here because we're looking at a weak acid. Okay, we had a W when we were looking at the equilibrium for water. We're going to put an A here and we're talking about acids. But we calculate K's the same way. Concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balance equation. But remember again, water is a liquid. We don't include liquids in our K expression. So this would be our equilibrium expression for this weak acid. The larger K is, the more the forward reaction proceeds. So we're going to have more hydronium and more conjugate base. So the acid is stronger. If we're looking at a weaker acid, less of it goes through this acid ionization. So the hydronium and the conjugate base will be smaller and Ka would be a smaller value. So we can figure out the relative strength of an acid by looking at its Ka value. The bigger the Ka value, the stronger the acid. The smaller the Ka value, the weaker the acid. If we're looking at mostly product, which means the reaction proceeds to get lots of product and very little reactant at equilibrium, Ka is large and the acid is said to be a strong acid. But if only a very small percentage of the acid actually goes through this acid ionization, we're going to have mostly reactant at equilibrium. Ka would be small, and we're looking at a weak acid. Now, this is just a picture. So if we were to look at a strong acid, okay, we've got our arrow going in one direction because it 100% dissociates. We start out with HA, and after the reaction, we don't have any HA anymore. We have all hydronium and A. The reaction went to completion. But if we look at a weak acid and we start out with HA, only a very small amount of these HA molecules actually break up into A and H. We're going to have mostly HA at equilibrium. That's what we look at when we're looking at weak acids. So strong acids 100% dissociate. Weak acids only a very small percentage. Okay, let's look at some numbers. We don't have to memorize these. We'd always be given Ka values. But if we were to look at strong acids, remember these are the strong acids that we talked about before, okay? Hydroiodic, hydrobromic, hydrochloric, perchloric, nitric, sulfuric. These all have very large Ka values. They essentially 100% dissociate in water. If we were to look at these down here, these are all weak acids. Weak acids have small Ka values, and the smaller the Ka value, the weaker the acid. So big numbers, strong acid, kind of have the, oh, and then we've got the conjugate base would be stronger than, or would be weaker than the acid we started with. Okay, we've got kind of hydronium and water in the middle. Weaker acids have small Ka values, so their conjugate bases are going to be weaker. Oh, stronger. Sorry, stronger. Saying that backwards. So this is just a table here. It essentially is saying the stronger the acid, the weaker the base. Okay, so here we've got our strong bases down here, and we've got our strong acids up here. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. They're opposites of each other. If we look at an acid, we can write a Ka expression, concentration of products over concentration of reactants, raised to the power of the coefficient in the balanced equation. So we want to look at strong acids versus weak acids. So if we have a strong acid, Ka will be large. If we have a weak acid, Ka will be small. If we look at the equilibrium position, strong acids almost 100% dissociate, so the equilibrium position will be all the way over on the product side or towards the right. Whereas weak acids, the equilibrium position is going to be on the reactant side or all the way over on the left. If we wanted to look at the ratio of the hydronium ion, hydrogen ion, to the acid initially, for weak acids, that ratio is large because we essentially don't have any of the acid left. It's all become hydrogen ion. But if we look at a weak acid, at equilibrium, most of it will be in the acidic form and there'll be very little hydrogen ion. Now, when we talk about the strength of the conjugate base, the stronger the acid, the weaker the conjugate base. And for the reverse, the weaker the acid, the stronger the conjugate base.